All right. Good morning, everyone, and welcome to Keep Middlesex Moving webinar series. Before I hand this off to our host, Bill Neary, I wanted to go over some housekeeping details. Mark Warner will be sharing his presentation via our share screen. If you would like to ask a question, please use the chat feature in your screens. Once the presentation is complete, I'll go through the questions as they were received. This webinar will be recorded and it can be sent to you along with the presentation at your request. And now I will hand off the webinar to our Executive Director, Bill Neary.
Thank you, Christina. Good morning. I want to introduce Mark Warner, who's the Vice President of Gabel Associates. This is a focus on developing market-leading energy policies and supporting clients implementing advanced pioneer projects. Mark is focused primarily on the emerging electrical vehicle market and is recognized throughout New Jersey and throughout the country in his EV market development policies. He's also very much involved in utility-sponsored electric vehicle programs. Mark leads research and policy development work for Charge EVC in New Jersey, including work to pass the recent landmark EV bill. Mark previously served as Director of Energy at the Sustainability Institute at the College of New Jersey, and building over a decade, I guess closer to 15 years of experience running one of the first solar energy companies in the Garden State. Mark, we're also very happy that you get to serve as a member of our all-volunteer Board of Trustees and the Keep Middlesex Moving Board. So I want to thank you for joining us today. I know your experience to try and condense it down to something that all of us can understand shows how much talent you have. And at the same time, I want to say that you not only talk the talk, you walk the walk. You live with these electric vehicles. So thank you, Mark. Thanks for joining us. I'm passing it off to you. And like to remind people, if they have questions, put them in the chat room.
Thank you, Bill. Good morning, everybody. Thank you so much for joining us this morning. Our topic today is a little more broad. We wanted to spend a few minutes talking about this thing that a lot of people are talking about called the smart grid. There are so many changes going on in our energy infrastructure, and we wanted to spend a few minutes talking about those broader changes and how that translates into what we're all doing today in terms of our overall energy use, technologies that we're using, and indeed new applications like electric vehicles. So what I'd like to cover today is I'll talk a little bit about the electricity grid as it is today and what it's likely to look like tomorrow based on all these changes that are underway. I'll talk about why these changes are happening, what are the underlying pressures. We'll talk through a little bit what some of the key technologies are that are making these changes possible. And then I'll give you a very high level update on where New Jersey is right now in starting to develop this grid 2.0, if you will. And we'll spend a few minutes at the end on, in a little more practical sense, what it means for you. What kinds of things should you be thinking about in terms of your energy use, your energy architecture, and so on. And we're definitely going to save time for questions at the end. So feel free to post your questions into the chat box, and we'll make time for those questions and discussion after we get through the slides. So let me start with what the grid looks like today. And most of this discussion is going to be focused on the electricity infrastructure for reasons that will become clear in a moment. So let's start with understanding what the current grid looks like. And conceptually, it's worth thinking of the current grid as, in essence, a straight line. We have a bunch of generation, power plants that generate electricity. They feed that electricity into the large transmission systems. Those are those great big giant towers you see marching across the landscape with big fat wires, bringing that electricity out to the rest of the country. And then those transmission systems then feed that electricity into the local distribution system. Those are the poles running up and down our neighborhoods and thoroughfares in New Jersey, owned by the utilities, that then deliver that electricity into our buildings, our homes, our office buildings, our shops, and so on. But there's a relatively straight line from the generation of that electricity through the transmission and distribution system directly to consumers. And the key thing about the current grid is that it's a giant synchronous machine. And what I mean by that is that the generation of electricity has to stay in perfect lockstep with the consumption of electricity. So conceptually, every time one of us flips a switch, there's a power plant somewhere that has to work just a little bit harder. Now, that's not exactly true technically. There is some headroom in the grid, but as multiple people consume more electricity, the generation plants have to increase their generation to stay in lockstep. So the grid today, most of those generation assets are what we call dispatchable, meaning that you can turn them on and off at will. And most of them are based on fuel, whether that's a nuclear fuel or increasingly or very commonly fossil-based fuels. That energy flow is mostly one way. It goes from the generation assets down to the point of consumption. And the control is mostly predictive. We have enough information that we know with a fair degree of accuracy how much electricity is going to be consumed at 10 a.m. a week from now. And the scheduling of those power plants happens fairly far in advance based on those predictive models. But the downside of that is there's very little adjustment that's made in essence in real time. And the reliability and the quality of the grid depends on our ability to do that prediction fairly accurately. That's a consequence of the fact that in the current grid, there isn't a lot of real-time information flow. And the other consequence of this particular architecture is that most of the entities in this system are either generators or consumers. And as we'll get into the discussion, you'll see how each of these elements are changing when we start thinking about Grid 2.0. So here's an introduction to what the emerging grid is starting to look like. Let me just preface this by saying that, the energy infrastructure, the markets, the technology providers, what it physically looks like is going through massive change right now. And as you'll see when we go through this presentation, there are a lot of reasons why that's the case. But the picture that I think it's worth having in mind is if the current grid is sort of best conceptualized as a straight line, the new grid, the grid of tomorrow, is better conceptualized as either a circle or a mesh. And the diagram on this slide here is a very typical representation of what the Grid 2.0 will look like. Much more diverse connectivity between all the different elements participating in the energy market. And that connectivity includes both the flow of energy, but also the flow of information. So the smart grid of the future is going to be much more integrated and interactive than it is today. It will include a much more diverse generation portfolio. Energy will be flowing in multiple directions rather than just sort of the one-way flow that we have today. At any point in this network, energy could be flowing in one direction or the other. And the control will be much more adaptive because we have a lot more information flow in this more advanced grid of the future. We can start to adapt the operation, both the generation assets, but also the loads to stay in sync with each other more adaptively in real time. And once we can do that, we can start to optimize the operation of the grid much more. And we'll talk about that a little bit more. And then one of the big changes is in the current grid, there's almost no storage, especially here in New Jersey. So when you think about it, every commodity on the planet is stored somewhere. We mine petroleum, for example, and we put it into giant tanks so that then we can take petroleum out when we need it. Same thing with food, same thing with almost any other commodity that you can imagine. But electricity is the only commodity on the planet that has to be produced the instant that it's needed. And that synchronous nature is what it makes it complicated and also makes it fairly expensive. But what's changing is because the cost of batteries has now dropped so fast, we can start to put storage into the grid. And now the generation assets can run on a schedule that makes their generation optimal. And then we can pull from the batteries to serve the loads, whatever that load might be. So we can now decouple generation from consumption. And that change by itself changes everything. So what we're going to talk through is some of the drivers behind this transition, some of the technologies involved with making this work. And then we'll get down to, in a more practical sense, what it means for us in the real world. The main thing to keep in mind is, physically, the grid of the tomorrow will look very much like it does today. There will still be wires running up and down the roads. but it will operate very different than it does today. So it's not just a change in technology, it's a change in the way the grid is operated and the benefits that result from that. So let's talk about a little bit about why these changes are happening. First of all, in New Jersey and in a lot of other states as well, we have significant commitments to clean energy, meaning reducing our greenhouse gas footprint, reducing our environmental footprint overall, including things like water and other non-greenhouse gas pollutants, and equity goals. In general, the goal is to get to zero carbon as quickly as possible. Many of you may have noticed that President Biden just announced new goals for the US last week as part of re-entering the Paris Climate Accords. And the targets he's establishing are that we're getting to a 50% reduction in greenhouse gas emissions by 2030, which is only 10 years away. So this is a massive set of new goals that require that we change the way we generate, distribute, and use energy. And when you think about what that transition is going to look like in New Jersey, there's really three things that we need to do. One, implement as much energy efficiency and conservation as we can up to the point where it's practical. Number two, electrify everything. Just about everything that currently uses fuel is a source of greenhouse gas and other pollutants. And we need to eliminate that fuel use in order to eliminate those emissions. And the way we do that is by electrifying everything. Now, obviously, there's a lot of things in our world that are already electric, but the new things that we're going to electrify are primarily transportation, so electric vehicles, electric trucks, and so on, and making the heating of our buildings more electrically based. Now, that probably won't just mean simple resistance heat, the way we would have done it 30 years ago, but using newer technologies like heat pumps, for example. So if you think about it, if we're really going to electrify everything as part of reducing our greenhouse gas and environmental footprint, that represents a massive increase in electricity use. Just think about EVs for a second. Ultimately, when we get to 100% of our cars being electrified, that means we've displaced the entire petroleum infrastructure with increased use of our electricity infrastructure. So that's a big increase in our use of this existing grid. So first step is efficiency and conservation. Second step is electrify everything. And then the third step, in parallel with both of those, is to decarbonize generation. And that means especially increase the use of renewable energy. Now, that's a whole new way to use our grid. That's one of the primary drivers around why the grid needs to change. And the reason is because it turns out that things like solar and wind are fundamentally different than our traditional resources like a gas-fired power plant. We can't just replace the existing generation with new, cleaner generation. We need to change the grid in order to make that possible. The reason is that those renewable resources are both centralized, like our power plants today. So we are going to have big wind turbines off the coast of New Jersey, and those look a lot like the big centralized power plants we have today. But it will also include a lot of distributed generation, especially solar. The other difference is that those renewable resources are intermittent. I mean, when the clouds come over, the amount of solar generation goes down just a little bit. So we have to be able to deal with that. And obviously, things like solar and wind, they generate electricity when the natural resources are available, when the sun is shining and when the wind is blowing. And that's not really anything that anybody can control. So we need to transition from a set of predominantly centralized resources that we can turn on and off at will to a set of centralized and distributed resources that have their own dictated generation profiles that are quite different from when we naturally consume that energy. So once we've evolved the grid to be able to accommodate those renewable resources, there's a lot of other things that we can do as well. One is that there's an opportunity to optimize the way we use the grid. As it turns out, the current grid is not very efficient. The way to think about that is that the majority of the grid today is designed around the peak load. The analog I like to use is the parking lot in Walmart. You know, the size of the parking lot in a Walmart is sized based on how many people show up on Good Friday. And then for most of the rest of the year, a lot of that parking lot goes unused. So if you design something to the peak load, that naturally means that a lot of that asset, whether it's an electricity grid or a parking lot, is going to go unused a lot of time. Well, that's the way it works in the grid today. The entire grid is designed around peak load conditions so that we can make sure that people get the power that they need even during a peak time. But it means that the use of that asset is not very efficient. We have an opportunity to now be more optimal. Once we've decoupled generation and consumption, we can increase the utilization of the grid, and that means that everybody's costs go down, which is a good thing. There are also increased expectations from both regulators and consumers, especially around reliability and resiliency. As more and more of our economy becomes based on the electricity system, we need to make sure that the grid is extremely reliable and that when outages happen, we can recover from those outages very quickly. So we need to evolve the grid to absorb or be able to support these renewable energy resources. That changes the way we use the grid and allows us to optimize that loading and reduce costs. And it allows us to increase the reliability as well. Once we've done those things, we're then in a position to start to accept some fundamentally new energy applications. And one of the best examples of that is electric vehicle charging. That's an entirely new load that didn't even exist mostly 10 years ago. And that's not just another light bulb or another load. That's actually a very smart, intelligent device. And we can use that load in a very different way in the future than we would have done in the past. So I'll talk more about that in a few minutes. So these are some of the factors that are motivating the transition from the grid that we have today to this more advanced grid that will be coming in the future. So here's some of the key technology components that will make that transition possible. First of all, a more advanced metering system. So as we're all familiar with, there's a utility meter on the side of our building, whether it's a home or an office building, and that meter measures the consumption of electricity. But when you think about it, for most of us, the utility doesn't actually know how much energy used until that meter reader comes out at the end of the month. So the utility is in essence operating blind most of the time and doesn't know what the actual consumption is until after the fact. So what's happening now is that obviously with the advancements of telecommunication technology and computers, there are much more meters that now allow us to measure that consumption in real time and to report it to the utility on a much more frequent basis. That means the utility can get a more granular perspective into what consumption is. So for example, for residential buildings, we can see what their time of day usage is. And to build that metering network, in order to do that more advanced metering, we have to build a whole new data network to support it. And it turns out that once we've done that, there are a lot of other things that we can do with that network. So just imagine that every telephone pole out there also has sensors that allow you to measure things like traffic. We can do real-time measurement of traffic patterns and use that to be smarter about the timing on traffic lights, for example. So there's a long list of non-energy uses that will come out of building this more advanced metering infrastructure on top of the benefit of giving the utility real-time insight into what consumption is and more granular insight into what consumption is. In parallel with that, there will just be more monitoring and instrumentation of all assets, even simple things like knowing what the loading is on a particular transformer. And that results in much greater real-time information flow. Rather than that predictive scheduling of generation and then knowing what consumption was after the fact, we'll be able to do both those things on a real-time basis based on much more robust information flow than we have today. And then, as I mentioned, the other big technology that's really driving these innovations is electricity storage. That's something that we didn't even really have even 10 years ago or 5 years ago, but now is becoming available and the costs on that are dropping very quickly. And as I mentioned, once we start to introduce storage, then a lot of things become possible because we can decouple that consumption from generation. We will start to see, because of this increased information flow, because we have more intelligence built into the network, we will start to see more demand response programs and more dispatchable loads. Demand response means that when we get to a peak time, in order to avoid the costs associated with that peak, the utility could send out a signal and people could choose to reduce their consumption at those times in exchange for some economic compensation. And similarly, there are a lot of loads now that are really dispatchable, meaning that we can choose when to do it rather than just letting the load happen whenever it naturally happens. A good example of that is vehicle charging. Natural charging would be, we all get home from work and we plug in our electric vehicle and it starts charging just like our phone. But what we could do is, rather than it start charging right away, that vehicle is smart enough to schedule that charging during off-peak times in order to mitigate impact on the grid. So those kinds of information-based load management systems allow us to optimize the loading on the grid, and as a result, we can reduce costs. There's a new concept that some of you may have heard called microgrids. A microgrid, just think about today, when the public grid goes down today, basically we're all out of business until that grid comes back up. Microgrids is a way to, in essence, carve off your own small part of the grid. And if the public grid goes down, you can separate from the grid and operate independently of the public grid, at least on a limited basis. So there may be some generation assets on your property. There may be storage on your property. There will be what's called an islanding switch that allows your building to separate from the public grid. And that ability to operate independently introduces a lot of potential benefits around managing the loads, improving reliability, lowering costs, and so on. And then in parallel with all these technologies, there's a lot of behind the meter things becoming possible. First of all, one that we're all familiar with here in New Jersey, which is on-site solar, being able to put your own solar panels on the roof and plug that in, behind your existing meter and generate some of your own electricity. Batteries, as I've already mentioned, and increasingly on all of our properties, we have smart controls. We can monitor consumption in real time. We can tell different devices when to operate in order to manage those loads more intelligently. The best example of that is many of us have put smart thermostats into our home, and we can now establish a programmed schedule on what we want the temperature in the house to be. But those thermostats are smart enough to modify that profile based on whether anybody's home or not, for example. So if you start to scale up those kinds of ideas, you can see how it results in a very different infrastructure than we've got today. Now, the thing to keep in mind is I just went through a list of relatively new technologies that are just becoming available, and adoption and deployment of those new technologies will be happening in parallel with ongoing reinforcement and growth of the grid. As I mentioned, if we electrify all of our vehicles and we displace fueled heat with electric-based heat, that's going to increase the amount of electricity consumption. So there's a lot of expansion and reinforcement of the grid that's going to be necessary to accommodate that additional load. And that growth and reinforcement is happening in parallel with these advanced technologies. So I think the way to think about this transition is just imagine that the public electricity grid is growing and getting stronger and more robust and has better controls and headroom in parallel with new technologies at the same time. Now, as I mentioned at the very beginning, you'll notice that I've mostly talked about changes to the electricity infrastructure. If we wanted to talk generically about how our overall energy architecture is changing, we need to think about that in the context of our clean energy goals. As I mentioned, if the goal is to dramatically reduce our carbon footprint, that means dramatically reducing our use of fuel as well. So as we look out over the next 2 to 3 decades, our energy infrastructure is going to become predominantly based on electricity. And so thinking about how our energy architecture overall is going to evolve ends up focusing primarily on how our electric infrastructure is going to expand to take on the functions that are provided by other things like delivering petroleum fuel to vehicles, for example. So those are some of the technology drivers. Let me give you a a quick update on where we are in New Jersey in making all this real. As you might expect, we've spent over 100 years building the electricity grid that we have today. In fact, the grid in New Jersey is one of the oldest in the world. We had this guy named Thomas Edison that actually lived right here in New Jersey. And our grid is actually one of the oldest and most developed in the world as a result of that. And those changes that I just talked about are going to take decades to do. I mean, we're talking about changes that are going to roll out over the next 20 to 30 years. New Jersey is at the very beginning of that transition. And here are some of the things that are starting to happen now. We've already had energy efficiency programs in the state for about 20 years, and that will continue. We are also deploying a lot of renewable energy in New Jersey, mostly solar, both distributed solar and more centralized solar power plants. And we are now starting the development of offshore wind. That's what OSW stands for. So approximately 7 miles off the coast of Atlantic City, work is starting to develop large wind turbines that will develop a massive amount of electricity based on the wind going offshore. Turns out New Jersey has some of the best wind resource in the world right off our coast. So both energy efficiency and conservation efforts and dramatic increases in use of renewable energy are already well underway in our state. Advanced metering infrastructure, which a lot of people refer to as AMI, we are actually just at the very beginning of that. Some other states have been implementing that literally for years. New Jersey is just starting to replace some of our old dumber meters with these new advanced metering infrastructure that involves, as I mentioned, both changes in the actual meter, but also building out this whole new data network to allow the utility to collect all the information from those meters. New Jersey is also at the very beginning of starting to introduce storage, primarily battery-based storage. Some goals have been set to build a significant amount of storage in New Jersey over the next few years. But to be honest, that is really just beginning in the state. So we have a lot of exciting new work to do to figure out how to develop all that storage capacity that I've been discussing. And the other one is starting to develop these smart loads that I mentioned, basically consumption that benefits from real-time control. So smart thermostats is a great example of that, as I mentioned, beginning to participate in demand response programs as they emerge. The other one, a lot of people are now either in their home or in their office buildings starting to look at electric vehicle charging. And along the lines of what I've been talking about, there's in essence 2 different flavors of that. There's very simple, if you will, dumb charging, but then there's also something that's a little more intelligent that's called managed charging. And the advantage of that managed charging is that ultimately those vehicles could provide bidirectional flow, meaning that sometimes during the day, the vehicle will be taking energy from the grid to charge its battery. And at other times, primarily at peak times, the electric vehicle would be putting energy back out onto the grid in order to help displace generation at peak time. So think about this synergy. Think about an office building that's got a huge solar array on the roof. It's now generating a ton of electricity in the middle of the day, between noon and 1 o'clock. And if you've got a bunch of vehicles that are now plugged in at that office building, they can be absorbing a lot of that solar energy and storing it for later use. And then later in the evening, even after the sun has gone down, when the peak in the grid actually emerges, those same vehicles can now reverse the flow and put some of that solar energy that was collected during the day back out onto the grid at a peak time. So that's an example of what I meant earlier, that if you were standing right at the edge of that building, between where the building connected into the utility, sometimes information would be flowing in and sometimes information would be flowing out. And you can imagine how that's a profound change in the way the grid needs to operate. And it also allows us to accommodate this whole new electric vehicle load, which is substantial. in a very efficient way without inducing a lot of additional costs. And then as we get a little bit further down the road, the state is just starting to recognize the need to displace fueled heating, either space heating or water heating, with heat pumps. Heat pump technology has been around for a while, but it's a relatively new recognition that that technology is going to be instrumental if we want to reduce the greenhouse gas footprint associated with heating our buildings. So those are things that are already underway in New Jersey. Things like energy efficiency and solar have been around for a while, but are still growing. And some things like storage and AMI technology are really at the very earliest phases of development. And I'm sure as we get into the next few years, there will be other new things that we need to accommodate as part of this new architecture. All right, so that's a lot of sort of discussion about where we are today and what's coming. What does it mean to you? What are the benefits for me as an energy consumer as we move to this new state-of-the-art smart grid? Well, first of all, the smart grid in New Jersey will allow you to reduce your environmental footprint and your greenhouse gas emissions, and also improve public health. I want to emphasize that second point because I think a lot of us have gotten in the habit of thinking about things like solar and wind as just a way to reduce greenhouse gas emissions and to tackle climate change. But it's really much more than that, because it also reduces the environmental footprint associated with generation and the environmental footprint associated with vehicles. All the air pollution that comes out of our tailpipes will ultimately be eliminated through the combination of electric vehicles running on renewable energy. And that has profound public health impacts. In fact, a study, a very big, credible study just came out recently that suggested that as much as 1 out of every 5 deaths on the planet are related to air pollution. And so reducing the pollution associated with our energy use certainly reduces environmental impact and greenhouse gas emissions, but we should also recognize that it's an improvement in public health as well, directly impacting things like asthma, cardiovascular disease, and so on. In addition, the smart grid will ultimately help you lower your energy costs because we have a much more optimal grid, and it should help you improve your reliability and resiliency. And then lastly, as this grid starts to evolve and your use of that grid starts to become more sophisticated, that will prepare you for some of these new applications, such as electric vehicle charging. So what can you do now? A lot of those things that I talked about are admittedly things that are going to play out over several decades. For those of you that are interested in jumping on the smart grid bandwagon sooner, here's a list of things that you can do. First of all, there's still plenty of energy efficiency work that many people can do. LED conversions are very, very feasible now and can lead to significant reductions in the absolute use of energy, as well as other traditional conservation measures. Everybody should be putting in smart thermostats, smart meters, and building management systems so that we can get to the point where we have real-time information flow on energy use, and then start thinking about the longer-term transition to heat pumps for heating. So if you're about to do a large capital project to replace an HVAC unit, at least consider the possibility of whether it makes sense to use a heat pump for that transition. Look at behind the meter opportunities, whether it's putting solar on your property, adding batteries to reduce your peak load or to shift how solar can offset your consumption. And if you're looking at electric vehicles, look at smart EV charging infrastructure, which is a really big priority in New Jersey. New Jersey is one of the leaders in the country for electric vehicle adoption. The state has set a formal goal to get 330,000 electric vehicles on the road by 2025. That's only 5 years from now, and at least 2 million vehicles on the road by 2035. So there's a massive amount of electric vehicle growth happening in the state, and we'll need to build the charging infrastructure to support that. And we want to do that in a way that aligns with this new, more intelligent, more advanced smart grid so that we can accommodate this new electric vehicle load without inducing a lot of additional costs. And then lastly, I didn't spend a lot of time talking about this, but the market itself is getting more complicated. It's not just the utility anymore. Many of you may be familiar with making use of third-party supply arrangements. So yes, the utility is going to physically deliver your electricity, but where you buy that electricity from is up to you. You can enter into contracts to choose your supply, including a source of renewable energy if you want. And there are a growing list of third-party services where you may be part of an energy aggregation program or part of a large peak management program, for example. So you can imagine a third party that basically manages the peak load of a whole collection of properties and then economizes that value into the energy market. So keep in mind as this grid begins to evolve that it's not just about what the utility does, it's the utility in addition to other third-party suppliers that may provide new services for helping you manage your energy consumption or where your energy comes from. So that's what I had in terms of prepared remarks. I'd be happy to answer questions, have discussion, and if anyone wants to get in touch with me, feel free to reach out through email. You can get me at mark@gabelassociates.com.
Thank you, Mark. That's it's what it does. I think it inspires us to think about how different the world is going to be. This grid. I guess I was more curious if the right word is bidirectional stuff. And using your Walmart analogy, is it? I guess you can have a large building like a Walmart or an office building where people don't necessarily need a fully charged vehicle that can then charge. If they only 200 miles of range and they only need 30 or 40, they can theoretically plug their car in outside their office or outside the store and recharge and provide the energy to that building and get the discounts for whatever that works.
That's exactly right. And those kinds of projects are actually really being done now, especially in California, where the electric vehicle population is so much higher. Think about it this way too. As you mentioned, Bill, the range on the most popular electric vehicles today is about 200 miles. So when you leave in the morning with a full battery, you'll have at least 200 miles worth of range. Most of us on average drive 20 to 30 or 30 to 35 miles a day. So that means when you get home from your workday, you will probably have at least 150 kilowatt hours of electricity already in that battery. Now, the peak time in New Jersey is somewhere between 5 and 6 o'clock in the afternoon. So if everybody comes home from work, plugs in their car at 5 p.m. and already has a bunch of electricity in their battery, they can then dump that electricity on the grid. And that means we don't have to engage those peaking power plants that are very expensive. So it fundamentally changes the way the grid operates today, and it allows you as an electric vehicle owner to actually get paid as a power plant rather than just being a consumer of electricity. So it really is a different world.
Will we need like additional wires or something or towers to be able to send the power back to the grid? Or how's that? I'm not sure exactly logistically how it would work.
Yeah, the grid is still, the physical delivery is still going to be mostly through wires, through physical wires. So when you come home, you're going to physically plug your car in, but the information to control that transaction is going to happen over the internet as we know it today. So your electric vehicles will likely be communicating with the utility about, is now a good time for me to dump some of that electricity or not? So physically, it will look very much the same. It's still going to be a lot of copper wires, but the way the grid operates is going to be based on a whole new information flow that doesn't exist today. That's what's really changing.
I guess that's my question about the dumping part. Will they need wires to take it back to the grid? I mean,
yeah. So when you plug your car in today, electricity can either flow into the car over that wire or out of the car onto the grid over that.
Okay.
So that same charging cable can go in either direction. And by the way, it's not just providing power to the grid. I'm actually going to set my home up here to be able to do this. I have a solar system in my home. I have an electric vehicle at my home. And the technology is now just becoming available that I could disconnect my home from the grid and run my home off my electric vehicle. So every home that has an electric vehicle in the garage can now, that electric vehicle could now serve as a backup generator. So electric vehicles are great for a lot of reasons, but it may be that one of the most interesting aspects is that it allows our homes to operate for some period of time when the public grid goes down. So it's a
Amazing.
resiliency improvement as well.
That'd be perfect during storms and things like that. And also, I'm thinking about even the major generators like hospitals and stuff would be able to provide additional ways of, to store the power.
That's right.
That's an incredible thing.
That's exactly right.
I guess my question also is, with all these upgrades of the local transformers we see in our poles, probably going to have to be upgraded also.
Absolutely. If you think about like the cans on the poles or the little green boxes on the corners of our neighborhoods, most of those are probably going to need to be upgraded over the next 10 to 20 years just to accommodate all this additional electricity flow associated with vehicle charging, and even more so if we start to electrify building heat. So yeah, a lot of those transformers are going to be upgraded because we're just using electricity more. And the opportunity here is that we can now put in smart transformers rather than dumb transformers. I remember I was amazed when I first learned that most of those transformers, the utility doesn't know exactly how much energy is flowing through that transformer in real time. It's, as I said at the very beginning, it's sort of a much more predictive basis for running the grid. But now if we're going to upgrade those transformers, because there's a lot of EV chargers in that neighborhood, we can put in smart transformers so that the utility knows what's really going on in real time.
Mhm.
Well, we all know if you get a pinhole in your pipes for water, that little bit of water coming out can add up to gallons and gallons and gallons of water over time. I imagine a little leak in some kind of electrical connection could do the same kind of thing. Just a faulty wire losing the electricity between the telephone poles is an expensive proposition for the utilities.
Yep. Well, I'll give you another example. We talked about, the smart thermostats and, smart AMI meters. Once we really have a detailed consumption profile for the home, you can actually compute how much insulation that home has in its walls. So if you know the temperature outside and you know the temperature in the home, it's basically sophomore level engineering to compute how much insulation there is. So you can start to identify home by home where it would make the most sense to try and focus more insulation, for example. So that's just one example of how we can use all this new information to be a lot smarter about how we become more efficient over time.
Amazing. Christina, do we have any other questions coming in?
We do. We were able to connect to Facebook, so we did get a question in through Facebook, which I'll read right now. And we have a few questions on our chat from one of our attendees, Bill Knox. Bill, I will actually let you ask those questions because we have a small, intimate group. So I think, let me just ask the first question from Todd Howard. How do we convince local governments to electrify everything? Metuchen is currently preparing to build almost 50 apartments. These could be completed in the next few years, yet these buildings will still have gas stoves, heat, etc., and will have no solar infrastructure. How do we change this?
That's a really good question. Thanks for asking that. And I think the answer is we're going to go through phases. The way policymakers like to make that happen today is providing incentives, in essence, incentives that will encourage people to do what we want them to do. So the state will provide money to, put in vehicle charging infrastructure or more efficient boilers or solar systems. At some point, the answer is the codes and standards that dictate what gets built will start to change. So for example, as we're now implementing formal greenhouse gas reduction goals, and we may see some of this happen at the federal level as well, given the national priorities now for climate response. The real answer longer term is that we start to tighten up the codes and standards that dictate what gets built. I mean, right now, you can't get a certificate of occupancy without meeting basic requirements around you have to have flowing water, you have to have an operating toilet, and so on. Similarly, at some point, there will be additional minimum standards regarding efficiency and some of these other advanced technologies that I've been mentioning. You can imagine that we start requiring buildings to have these smart meters, to have smart thermostats, to have built-in storage with resiliency features and so on. So in the short term, it'll be motivated more by incentives and awareness building. Medium term, I think we're going to need to update our codes and standards in order to really, encourage everybody to make those transitions.
Mhm, mhm. Okay, I'm going to allow Bill to talk. Let's see, Bill, can you hear us?
Yes, I'm unmuted as well.
Okay.
Good morning, Bill.
Hi, Mark. I have loved this presentation. It's just so well organized
Thank
and
you.
well presented. I'm a member of Somerset County's Energy Council and but I'm the public dummy, or they call me the public generalist. I'm the only person on the Energy Council with no technical background, but I continue to learn. I thought this was just a superb presentation about what we can look for in the future grid. So my first question was that I had a utility executive tell me that New Jersey probably has no neighborhood where everybody could be like you and me at this point, having an electric vehicle that needs charging every night. The wires, the transformers just don't have the capacity, so that there's a huge infrastructure investment that needs to be made in what's called the last mile, the wires that carry our power from the transformers in our neighborhoods to our homes. Would you agree that if everybody in the neighborhood has one or two Teslas or some other EV in the garage, that's just an enormous additional demand on the net?
That's a great question, Bill. Thanks for asking that. The answer is it depends. And it gets back to what I mentioned. There are really two different ways to charge your vehicle. One is natural charging, which is, as you might expect, everybody comes home from work, plugs in their car just like they do their cell phone. And that means everybody is starting to charge at the same time. And that new vehicle load is now on top of the load that already existed. If that's what becomes dominant, then yes, you're absolutely right. There's going to be massive reinforcement and growth in the existing infrastructure to support that charging load. And I've done, as part of my work here, I've done a lot of modeling on exactly when that starts to kick in. And the short answer is we have a fair amount of headroom for at least the next couple of years. But
Okay.
at some point, somewhere around 5%, when we get to the point that 5% of the cars on the road are electric, you start to have a more systemic need for that reinforcement. But the other option is we don't have to do it that way. It turns out, I'll give you a statistic. The average electric vehicle at home stays plugged in for about 8 hours, but they only charge for 2 of those hours.
Yep.
So that difference between being plugged in for 8 but only charging for 2 means we have some flexibility in when that charging happens. So if it turns out that we can create markets and programs and incentives and so on, that charging happens at 2 o'clock in the morning rather than 5 o'clock in the afternoon,
Right.
you don't really need much, if any, reinforcement. So that kind of managed charging program both defers when that reinforcement would be needed, and it may eliminate a lot of it as well. So the real question, and this is a lot of my work right now in multiple states, is really about this issue. The question is, would we rather spend money now creating managed charging programs that encourage people to charge at the right time so that it doesn't create additional load? Or are we going to not do that and then just spend money on more copper later? That's the real choice. All right. So
Okay.
when you think about the example I like to use is air conditioning. You know, when we all got back, not we, but when our ancestors got back from World War II, everybody put air conditioning into their home. There was a massive growth of load that happened in the 50s and 60s and 70s related to everybody getting an air conditioner. And we just let people run their air conditioners whenever they wanted to. That's a lot of what created this very peak-oriented consumption profile we have today. We could make the same mistake with vehicle chargers. We could just let that be another load, let people charge whenever they want to, and then just build the system to accommodate that natural load, whatever it is. We all know right now, as that executive you mentioned referred to, that would be really expensive. But this is 50 years later than that air conditioning load first emerged. We can now be much smarter. And the question before us is, are we going to do smart vehicle charging in a way that actually allows us to optimize the use of the grid? or are we just going to continue to do things the way we always have? That's the essential question.
Well, I have my Tesla set to charge at 2 a.m. in the morning for just that reason.
Yep.
But I think we're going to need some sort of a carrot in that you ought to be able to buy the juice a little cheaper at 2 o'clock.
Right. Well, you'll be pleased to know that all the utilities are proposing exactly such programs. I'm actually working to help design some of those programs. So two of the utilities, ACE and PSE&G, have been approved to offer residential off-peak charging tariffs. It's going to be about a year or so before those become available. But that's an example of what I was talking about, is that if you now sign up for that new tariff, you can charge your vehicle based on lower cost electricity than if you just did it the way you normally would. And if we get enough people signed up in those programs, we can actually accommodate a lot of additional load without building more copper.
Right. My second question to you was again on EV charging issues, but I'm wondering, the current lithium-ion battery technology gives us great batteries for sure, with prices continuing to become more reasonable. But there's a limit to how many charge cycles you can do. Anytime you're charging a battery, you are using up a part of its scheduled lifetime.
That's
and
right.
if EVs start getting plugged into these distributed energy systems, these smart charging and available resource systems where they can act to be backup storage while they're plugged in at the office or plugged in at home, that's going to wear out batteries faster, won't it? I mean, that seems to be inevitable unless battery technology changes.
No,
you're using up
you're,
some of your cycles.
Yeah, no, you're absolutely right. The battery lifetime is dictated by, how many discharge cycles it can go through before you start to lose capacity.
Right.
So you're absolutely right that using those vehicle batteries in other ways besides just moving the car will have an impact on the lifetime of those batteries. The good news, the reason I think it's still worth talking about all that stuff I talked about, is that batteries are changing dramatically. So the newer lithium-ion batteries, now have much longer life cycle projections than even 3 years ago. And I think over the next couple of years, we're going to be moving into fundamentally new chemistry. So, for example, solid state batteries. So there are people literally talking now about million-mile batteries, meaning that your car is going to come with a battery that will last for 1 million miles. And if that's really true, not on a single charge, obviously, but you could, you could charge it over, you could charge over and over and over again and run up 1 million miles worth of usage before the battery starts to degrade. That gives you so much headroom that you could use your battery in that way without, in essence, losing out anything in a practical sense. The other thing that I think will happen is, as you're probably familiar, Bill, as an EV owner, if you're a battery in an EV, that's tough duty. That's like being a racehorse where you have to run a race every day. And I think what we'll see emerge in the market is, as cars are retired and taken off the road, those batteries will be removed and repurposed into stationary storage. So we'll be taking all the batteries out of the electric vehicles and then building storage into the grid, which is a much less demanding duty cycle. So there's going to be a lot of interesting stuff happening with batteries overall.
Sure there will. Thanks, Mark.
Thank you, Bill. Thank you. We did have one other hand raised from Bill Amon, but now it is lowered. Let me just check. Let's see.
Well,
Bill,
while you're checking, I'm sorry, go ahead, Christina.
Bill, would you like to ask a question? You're unmuted as well.
Well, my question wasn't a question, it was a comment. When Mark was talking about air conditioning, I was thinking about Will Rogers said that air conditioners probably did more damage to this country because it made it possible for the politicians to spend the whole year in Washington, D.C. So nobody want to be in the summertime in Washington otherwise,
Yep.
Bill, Bill Amon, you're unmuted if you'd like to say something.
Yeah, well, I don't have a question. It's a great presentation, Mark, but just wanted to let Bill Knox know that I'm on the call with him as usual. I'm also on the Energy Council and also have a Tesla. So I guess one question I guess I could pose to Mark is, there's a lot of smart metering stuff out there. Everybody that has any kind of meter that does anything calls it smart. But the ability for meters to actually get signals to do time of day charging, reverse power into the grid, which utility companies they don't like reverse power into the grid, as you know. Is that stuff actually out there available yet? I know our utilities here wouldn't allow us to use it yet, but is it even developed?
It is available, but I would eagerly say it's very early stages. Some of those things, like the ones that you mentioned, are in what I would think of as pilot phases of implementation. Small scale, very early stage technology, not sort of scalable market wide yet. We have a lot of learning to do about a lot of these things, and that's why I think of this as something that's going to happen over the next 10 to 30 years. And we're in the early stages of some of those more advanced technologies. Some things like batteries, like you can go buy there are a variety of places, including Tesla, where you can get a battery that you can put into your home, either in conjunction with your solar system or not. You can get smart thermostats today. The utilities are just starting to roll out the AMI technology in New Jersey. So it's starting to happen, but to your point, it is very early stage.
Yeah, I'm concerned that we're going to roll out a technology that's going to be obsolete in 5 to 10 years, and then we're going to go through there'll be resistance to go through another technology change.
Yeah, I think we need to all just sort of join hands and recognize we're going to be in a state of continuous technology churn forever now.
Wonderful. And do the products are probably brand new here. Is any of this further advanced in Europe?
Somewhat. It varies quite a bit in Europe, but to be honest, the market models in Europe are so different than here. That might not be the best example. There are some technology choices that could be looked at, but the better example here in the US is California. So a lot of the things that I talked about, including bidirectional energy flows and things like that, are being trialed in California, and those are starting to scale up over time. So as with so many other things, I think we can look to California as sort of a bellwether on how these things are going to evolve over time.
Very good. Okay, well, unfortunately, we are out of time. I want to thank you, Mark, for taking the time to share your presentation with us. I'd like to thank all the Bills that are on this call. What are the odds that there are 3 Bills on a call of 9 people? So thank you to each of you and to everyone else that's on the call as well.
Well, and I'll point out that at least 3 of us that I know of have electric vehicles. So
exactly.
And I'll point out I get my electric bill every month. So there's lots of bills. There you go.
So I was able to record this video. So if anyone would like a copy of it, please let me know. I will email it to you. Mark, if you send me your presentation, I can also pass that along. Thank you again, everyone, for participating. Have a great afternoon, and most importantly, stay safe.
Thanks, everybody. Bye-bye.
Take care.
Bye-bye.